Up next is Matt Swann. Matt Swann is the Chief Security Architect for OneDrive and SharePoint team, and he leads an engineering team that is focused on defending customers. He's a 14-year veteran of the SharePoint team at Microsoft. He's passionate about intrusion detection, incident response, and digital forensics. Let's welcome Matt.
Thank you. All right, thank you. I have a fancy title, but I'm an engineer. I lead an engineering team. And so what I want to share with you today is how my team uses graphs to get more value out of the intrusion detection results, the alerts that we already have. My team operates with an agile principle, and so we try to build everything incrementally, right? We built intrusion detection. That was giving us alerts in free text. We learned how to take those alerts in free text and schematize them, and then we learned how to use those schematized alerts, that schematized data, to represent them as graphs to help our analysts make more value, get more value out of that. So that's what I'm going to walk you through today. So a little bit of background. My team is responsible for keeping your engineers, your organization's most valuable intellectual property safe in Office 365, in OneDrive, and in SharePoint. And so this is over 300,000 machines uploading security event logs and custom telemetry from our ETW agent to the cloud. Now, for us to deliver on our customer promise, detection in this environment needs to be accurate, timely, and comprehensive, right? And I measure that both by how quickly my engineers can get paged or how rapidly we can take automated actions when something malicious gets into the environment, but also my breadth of coverage across the kill chain. If I only have one alert that tells me that an adversary is, on his way towards an objective, that means I have something fragile, and that makes me worry, right? And so my detection pipeline probably looks a lot like yours. I've got Windows security event logs, logs from my custom agent. I've got ETW-based monitoring, network-based monitoring. And I take those detection results, I crack out the entities and the properties using something similar to the common eventing framework, but it's something we developed in-house. And we store this in a database, a columnar database called Azure Data Explorer. It's much like Elasticsearch. We do normalization to make sure that all of those column values have a consistent semantic meaning. So username is a username, not a domain, not a UPN. It's lowercase. Domain names are uppercased. Host names are always lowercased and normalized. And then we classify our detection results, our alerts, according to the fidelity of that detection. So we have many alerts that just give us context, right? We never page anybody about these, but we show them in context with other results so that our engineers, our analysts can make better decisions. Next, we have behavioral detections. And these are things that often happen just because an engineer is getting their work done or the environment has changed. Next, we have atomic alerts. And these are things that we always want to review whenever they happen in the environment. For instance, if someone installs a service on a machine, I want an alert that somebody's going to look at. And if that isn't happening across all 350,000 machines in my environment, I'm concerned. And finally, I have alerts. And these are that small population of extremely high fidelity things that as soon as they happen, they page an engineer, and we jump in and we respond. So if I'm going to get value out of this system, I have to be able to optimize for a couple of things. I need to solve three problems. First, my analysts need to see these results in context. Because otherwise, if I'm sorting by type of detection, and I'm just resolving all of the alert type A first and then alert type B next, that's maybe easiest to do. But if I'm not making the connections between three different alerts that happened on the same user or the same host, then I'm missing the story, right? I'm looking at page 37 of a novel, saying it looks good, ripping it out, throwing it away, but not considering the full arc. Next, my analyst time is scarce, right? I have hundreds of thousands of detection results coming out each day, generated from between 14 and 20 terabytes of security event logs and ETW telemetry every day. And I need to make sure that my analysts are looking at the thing that is most likely to be a true positive evidence of an intrusion when they start looking at that. Finally, I want to turn my engineers loose to add as many detections as possible to cover as much of the kill chain as we can see into. And if they're stymied or handicapped or handcuffed by the false positive, true positive ratio, then I'm only going to be able to add a certain small number of detections, and many of them I'll turn on and then immediately turn back off, unless I have some way to link these together and deal with them in a way that doesn't overwhelm my analysts. And here's where I use graphs. So there's two ways that I found that we can represent the events or the detection results that we already have as graphs. And I want to walk you through both of those. And the first kind is a causality graph. And here we're going to take two nouns and a verb, and we're going to use that to represent every event that goes through your system. So imagine for a minute that you have an alert saying a large amount of data has left a machine coming from a process and going to an IP address on the internet. Right? You could say, well, that's a noun, right? I've got a machine or a process. It's doing a verb. It's sending traffic. And where is it sending it to? It's sending it to an IP address, right? Noun, verb, noun. There's subject, verb, direct object. And this is really useful for forensics. And so this is where we started with graphs. At a BlueHat conference just like this about 5 years ago, I got distracted, opened my laptop, and started writing the translator that says, for a 4688 process start, extract the nouns, extract the verb, put that into a graph. And then, well, what's the next most common event type? I guess that would be a 4624 successful logon. And you work your way down the list of Windows event logs, turn them all into graphs, nodes, edges, insert them, and then voila, I have a bunch of dots and edges, and I can take an event log and show it to someone. And even an engineer who doesn't know that 4688 means Windows process start can follow causality and understand what happened before and after a malicious event. But that isn't really what I want to do in order to solve, the things here, right? I'm not looking at forensics. I'm talking about whether my detection results are useful and actionable. So something else I can do is called a hypergraph. Now I'm going to still take those nouns and verbs, but I'm going to extract entities instead. And say if I have a process that's uploading, I'm going to represent that process uploading event, that detection, as one node with a timestamp. And then I'm going to pull out all of the entities associated with it. Right? I have a process, I have a user on a machine, and I have the destination that it's sending traffic to. And I'm going to make this an undirected graph. Right? I can get from that IP address to that detection, or from that detection to that IP address. And the mental model, the reason that this has some affinity with me, is that this looks a lot like how, as an analyst, I would pivot between one detection and maybe the user that was compromised or the host that was compromised, and then go look at other things that happened on that user or on that host. So if you remember my detection journey, we started with just plain text alerts in our incident management system. The next thing we did, we schematized them, and we broke out host names and users and process names and detection types. Well, here's how we build that hypergraph. Right? We take a detection type on the top, connect it to entities. We do the same thing for the next detection type, and we reuse entities that are already in the graph. And likewise with the third. And when we're done, we end up with clusters or components, disconnected portions of the graph that are all related to those detections and those entities that have something in common. So this is a real graph of real alerts from Office 365 at a time when we had done a penetration test with the Office 365 Red Team. And we had just worked through this hypergraph model, and we had a hunch that if this model, if we imported this data into this model, that the adversary activity would pop out and be obvious. And so there's two patterns that you'll see throughout these graphs. On the right, each dot is a distinct detection type. Each gray box is an entity, a user or a machine. I have many distinct detection types firing on a relatively small number of entities. That's red team behavior. That's a true positive. On the right, I have one detection type firing on a whole bunch of machines and no other adversary activity there. Right? That, in our experience and in our mostly homogeneous, wide-scale environment, that's a false positive. This is a behavior change that happened on those machines that my system doesn't yet know about. And I need to tune it or add rules to damp that down. And so as a visual thinker, seeing this and seeing things that I intuitively knew were true about my environment or about the pattern of detections that I would get, seeing that pop out and suddenly be visual in a way that I can apply math to, well, it was amazing. It was a revolution to me. And so we call that clustering. I know for folks with a data science background, those are components, not clusters, and those mean different things. But I work with engineers. I'm an engineer, so clustering is a term that is a little more visceral and evokes the right image in lay people here. So we call each of those an incident. And then what we do is we take that cluster, we save it off, and then our engineers look at all of the results that happened in that cluster together. And they don't look at that in that graphical form. They look at it almost like Excel, right, in tabular form, where they can expand and collapse and link and filter and define terms, because that's the interface that shows them all the context and information that they need densely. And it works, it adapts to their phone, it adapts to their laptop or their desktop machine or very large interactive displays. And then we also merge clusters that are identical. So for example, these clusters have the same detections on them, linked to a handful of machines. Oftentimes, that's the same maybe new environment behavior that's happening on many machines. And so if we link that together, the analyst can see that this is happening and create rules for it to improve our detection fidelity. Now, once I have clusters, I can take actions on them. Right? One thing I can do is I can look for activity that is clustered together because it's environment-wide. And those environment-wide changes might be indicative of new features rolling out or new architecture decisions that have been made in the service. And my system can automatically say, you know, this is one of two things. This is either an adversary who has compromised 350 machines simultaneously, or this is system behavior, right? This is a new change that rolled out. I'm going to take an informed hypothesis, create a rule for it, and alert you that I've taken that action so that you have the opportunity to roll it back in case it's ransomware or a previously unknown vulnerability being exploited. But the other really powerful thing we can do is we can alert when clusters breach a score. And so now I can infer or synthesize a high-fidelity paging alert from a collection of low-fidelity behavioral or contextual detection results that were all linked together by entities in common. That begs the question, how do we score these things? So our initial tack at scoring these was to look at the topology of the cluster. And we said, I know I have different kinds of detection results, different fidelity ones. So I'll say that any cluster that contains an atomic result or an alert result, that cluster has to be triaged. But anything that has just one behavioral result and nothing else in it, that's anomalous activity but not malicious. It happens all the time. I'm going to ignore those. But if I ever get two different behavioral alerts, two different behavioral detections, low fidelity, on the same entity, that whole cluster suddenly became in scope for me to look at. Because that's the beginning of a story, right? We're grounding ourselves in the concept of a kill chain and saying that for an adversary to be successful in our environment, he or she needs to accomplish multiple stages of that kill chain between their entry point and their ultimate actions on objective. So I'm going to look for evidence that a story is taking place across the entities in my environment, and I'm going to pay the most attention to places where that story is most prevalent. And I'll use topology for scoring. So I'll say for each detection type in that cluster, I'll give it some points depending on if it's high fidelity or low fidelity, and I'll divide that point score by the number of machines exhibiting that detection. And so like the pink example on the right in my previous slide, if I have one behavior that happens on many, many, many machines, more often than not, that is a new system behavior that my detection system is overly sensitive to. I want to downvote that detection's significance. But if I have anomalous behavior that's happening on only a handful of machines, that is more significant to me, and I want to upvote that. But it turns out that although this has been working really well for us for the last several years, this has some disadvantages. And so what I would like to share with you for the remainder of the talk is what are the disadvantages that we've seen. There's 6 things that we're going to do this year to make up for those disadvantages and put in place a better scoring mechanism. And then I'm going to leave you with an open question that I have that I would love your help with. As someone who's an engineer and not a statistician, I unfortunately don't know the techniques that I don't know. And so there's problems that I don't know how to solve, but I'm confident that more than one person in this audience does. And so I'd love to listen. So one of the problems with my cluster topology scoring is that it treats every detection the same. It doesn't look at things like business value or kill chain stage. So why don't we take that into account? Right? So for when we think about scoring V2, I'm still going to use my graph representation to identify linked alerts. I'm still going to use some scoring or topology to decide what gets triaged. But then I'm going to rank these clusters more effectively based on what I know to be true about the environment or the detections themselves. So for example, the first thing I can look at is kind of obvious. And it's in fact embarrassing that we didn't think of this in the first place. Why don't I map each detection to its associated kill chain stage? And then when I see a cluster that has multiple hits along the kill chain, that tells more of that adversary story. And it's more likely to be a true intrusion. I want to promote those to the top. Likewise, if I see evidence of an intrusion on a high privileged asset, I care about that more than evidence of an intrusion on a low privileged asset or a low privileged user. So again, I want to rank some of those or bubble up, promote some of those detection results based on the business impact of those entities. Likewise, if I see many results in a short period of time across different entities, those are more likely to be part of the same story. When we do clustering, we look back at 7 days of data, and we do that partially because we want to give our engineers the opportunity to say, you know, I'm pretty sure this is benign, but I'm not positive. So I'm not going to mark this as system behavior or detection bug. I don't have enough evidence to think that it's malicious or even discouraged activity maybe by an engineer. I'm pretty sure this is okay. And because these are humans, human analysts looking at data, I don't want to force them into kind of a binary model in their mind that something is either absolutely fine or absolutely not okay. I want to give them the grace to say, you know, I'm 60% certain this is fine. None of my spidey sense is going off. I asked the rest of the team, they think it's okay too. But in the future, if we see other detection results on that same entity, we're going to show those okay detection results again in context. So that if that was the beginning of a story and I got a later chapter, I have a second chance to revisit it. So those 7 days of data is important to me, but I think sometimes it combines data together or events together that aren't part of the same story, right? And if I see a small number of things temporarily clustered together, I want to promote those up. One of the other problems I have with my existing cluster detection logic or clustering logic is that I might be missing a detection that spans adversary activity going from one machine to another or one user to another. And so what might be one very high scoring cluster gets broken up into two, and those clusters sync because they're missing that relationship. And so something that we need to solve in the coming year is how can I infer that activity on asset A, machine A, user A could be linked to this activity in this other cluster, because I know that there are some aspects of how my data center is designed that could allow privilege elevation from one to the other in a way that maybe I currently can't detect. Finally, detection likelihood and non-likelihood is something that we can incorporate. So imagine that you had a detection that said, hey, a new security-sensitive registry key has been added. Not all of those registry keys are going to be commonly touched, right? If you were to build the list of auto-start entry points, registry keys that can be used for persistence, that is an extremely long list. But day to day, you really only see 5 to 10 of those locations get touched. New scheduled tasks, new services being installed, new printers or DLLs. Very rarely do you see a new COM registration being created. So I don't want to treat all of those new auto-start entry point registry key alerts the same. I want to treat the ones where a new service is installed differently, because those fire quite frequently, in fact. Versus if I see a new COM object get registered, even though that's the same detection, that is much less likely to be benign behavior, and I want to promote that differently. Then I have the opposite problem, though, too. I already get a detection for a service being installed, and I get a detection for the registry key that creates. Those two detections link up and promote that cluster to get triaged every time. these guys always come in pairs. And so something that we need to do over the next year is to look backwards through our data set to identify these dependent events that always fire together, cluster them, treat them like one event, and rank them appropriately. Finally, last slide. I don't know how to combine all of those scores on a given cluster. I'd imagine I have one scoring mechanism that says, for this cluster, I see 3 things in different parts of the kill chain. So that gives me one score that I want to apply to the cluster as a whole. Next, I have detections that say, oh, this asset implicated in one of your detection results is very high value to the business. Promote that. Something else looks over here and says that registry key that's touched, that registry key gets touched all the time. Downvote that. How should I incorporate those individual detection boosts and boosts and sinks and the overall score that I want to apply to the cluster because of its relationships or the progress along the kill chain that I saw? I know there's somebody in the audience that can help me with this. I'd love to chat with you afterwards. And that's it for me. Thank you.